Hello everyone. This lesson will be the start of a new overall topic called polar coordinates, and specifically we'll be talking about the basics. So, what are polar coordinates? Well, it's a different coordinate system that allows us to do some different things than our usual coordinate system that we use. So kind of like we saw with parametric equations, polar coordinates allow us to do different sorts of graphs than before, like these. And graphs like these would be pretty hard to achieve with our previous knowledge. And now to get a better idea of what's going on, let's compare this new system, polar coordinates, with the kind of coordinate grid that we're used to working with. And we call those Cartesian or rectangular coordinates. So for example, you've seen a coordinate grid like this, right, with an x and y value. And then when we graph points on a grid like this, we have points like 3, 7, for example, where the left number is the x value and the right number is the y value, right, 3, 7. And with polar coordinates, we're still going to be working with pairs of numbers, but the numbers mean different things than before. And the grid we're working on is like this. So note that in both systems, we're working with the same 2D space, okay, points and graphs in the same 2D space, but we just think about those same points differently. And really quickly notice that, you could think of the grid on the left as being like rectangular, made up of squares, and the new grid here looks circular. And now specifically, how does this all work? So, in what we're used to, Cartesian or rectangular coordinates, the ordered pair, right, 3, 7, this left number, that's the x value, and the right number, that's the y value, right? So of course we start at the origin, and we go right 3, up 7. And that's the system we're used to so far. But now with polar coordinates, this left number is what we call the radial distance or the radius. Basically, it's the distance from the center of this point that we're about to graph. And then the right number is the angle, the angular coordinate. And as in the past, this angle means counterclockwise from 0 degrees, which is in the positive x direction. So 0 degrees is here. So what that means is this point is 60 degrees from 0 and distance 5 away from the center. So from 0, 60 is along here. But then starting at the center, we go out 5. 1, 2, 3, 4, 5. So this point right here is 5, the distance, and then 60 degrees is the angle. So let's discuss a bunch of quick examples. First up, we've got 6, 120 degrees. And so don't forget, we can have big angles as well. So 120 is from 0, it's here. And then 6. So start at the center, go out 1, 2, 3, 4, 5, 6. That's right here. This is 6, 120. But then the next one, there's something weird going on. It says -8. So what is a negative radius or negative distance? -8, and then the angle is 150 degrees. So what you do is you first start out by going to 150 degrees, so here, right? And usually, if the radius was positive, the point would be along this line somewhere. But now this negative distance means we go backwards. So going along this line, we go backwards in this direction by this distance, 8. So we did start at 150 degrees, but really we're going over here in the opposite direction. And so let's see here, 1, 2, 3, 4, 5, 6, 7, 8. So here is -8, 150 degrees. And now angles can be negative too. So up next we've got 10 and -90. So -90 degrees starting at 0. Usually with positive angles we go counterclockwise, right? But instead, for a negative angle, we're going to go the other way, clockwise. So starting at 0 or 360, and we go backwards 90, that's along here, right? And then this particular graph, it turns out the outermost part is 10, so 0 is the center, and if you count 1, 2, 3, 4, 5, this outermost part is 10, so that's where 10, negative 90 is. And then, of course, both the distance and the angle could be negative. So where is negative 3, negative 120? Well, first of all, negative 120, by the way, on this particular graph, each of these is 15 degrees. So then two of those is 30 degrees. So 30, 60, 90, 120. Negative 120 is along here. But then we go negative 3. So we have to go the opposite direction. So negative 120, but then negative 3. So 1, 2, 3. And negative 3, negative 120 would be here. And that is how you graph polar coordinates. Oh, one quick thing. Know that polar coordinates are not unique. So what does that mean? So here I've got 4 new points listed out, except they look like 4 different points, but they're actually all the same point in the sense that if you graph them, you'll find that they end up in the same spot. So let's see. First we got negative 5, 240. So 240 is here. But then we go backwards 5, so 1, 2, 3, 4, 5. Here's the point. What about the others? 5, negative 300. So if I go from 360, go backwards 300, I'll be at 60, and then positive 5. So yep, same point. So next we have 5, 420 degrees. And remember, with any angle measure greater than 360, that means we go at least once around the full circle and then keep going, right? So for example, start at 0 degrees and then go counterclockwise all the way around to get to 360. But then from 360, we go further counterclockwise to get to 420. So 360, and then 2 of these is 30, which would be 390. And then another 30. So 360 plus another 60 degrees is 420 degrees. And then again, from the center out 5, boom, of course, the same point. And then same deal with negative 5, negative 120 as well. Negative 120 is here, go backwards 5 to get to the same point. So again, all of these points are written differently as coordinate pairs, ordered pairs, but in our 2D space, they are the same exact location. Those coordinates are not unique. So now let's talk about polar equations, because of course there's going to be equations, right? Now, in our previous work with Cartesian coordinates, right, x, y coordinates, we would take equations like y equals, and then some formula involving x, and then we take that, make a table of points, and graph them, right? And that's exactly what we're going to do with polar equations as well. But now with polar equations, typically you'll have an equation like r by itself on one side, so r equals, and then some expression involving theta. So this is an equation that gives r explicitly as a function of theta. And so now we're going to take this polar equation and make a table of points, right? And so this table is already telling us, okay, use these theta values. And we can use these theta values to find the r values, the corresponding r values. And then, of course, that'll give us a point in each row to graph on here, right? So let's fill in the table. Notice that, from the table and the graph, we can tell, okay, we're supposed to be working with degrees in this example. So don't forget to be mindful about whether your calculator should be in degrees or radians. So if you use your calculator in degree mode to get the R values, this is what you should get. So here's the table you should get. Notice that a lot of the numbers aren't very clean. And then let's graph these. So be careful with graphing anything with distance 0, right? R equals 0, because this first point, remember each row is a pair, right, a point. We're graphing this point like, okay, 0 degrees is here, but then the radius is 0. So actually the point, if the distance is 0, the point just stays at the center, right? And then next 45 degrees. So 45 is here, and then 3.5355, we're just going to have to estimate somewhere between 3 and 4. So 1, 2, 3, 4. So very close to halfway between 3 and 4. So there. And then 95, 90, and then 1, 2, 3, 4, 5. So here. Next, 135 degrees, and then 3.5355. So around here. And then at 180, we're back at 0. So 180 is over here, but then radius 0 means we're back in the center. And then one interesting thing, you are going to find that if you graph the next 4 points, they end up being these 4 points that we already graphed, right? They end up being in the same place. So for example, 225 is here, but then minus 3.53, we're going to go backwards, and we're back at this point that we graphed already. Same with 270, negative 5. 270 is here, but then we go backwards 5. Boom. So, really we should be graphing more points, like in between 0 and 45, in between 45 and 90. In between each of these points we have. And if we did find more points in between and graph them carefully, you'd find that the graph is a circle like this. And furthermore, the circle completes at 180 degrees. And then from 180 to 360, the graph actually just goes back over the same circle again. By the way, when we're connecting these, be very careful with the order of the points, right? We start at the point we got with 0 degrees. And then we go to the point we got from 45 degrees, 90 degrees, 135, 180. And sometimes with the positive and the negative radiuses, it might be a little confusing to follow the points correctly, so be careful there. Now here's another example, and just a quick note about constant equations. So the equation here is r equals just 7, right? 7's a constant, and there's no theta. So what that means, how are we going to take this equation and plug in these theta values? Well, if there's no theta, you don't plug in any theta values, and it just means that the r value for each one is 7, right? It's a constant, as in r is always 7, and it doesn't change depending on the theta value. It just stays 7. So the table would be like 7, 7, 7, 7, etc., right, all the way down. And that means for every angle, we have a radius of 7. So 7's here, 7 there, 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 there. And it makes sense. Basically, it's saying the radius, the distance from the center, is always 7. Well, that's the set of these points. All the points whose distance is 7 away from the center. I need to get better at drawing circles. So that's how polar equations work when r equals a constant. And now, last topic of the day, converting between the two coordinate systems, Cartesian and polar, because of course we're going to be converting back and forth, right? And for this, remember that no matter the system, we're still working in 2D space, right? So let's say we're talking about a point out here. Well, here's the origin, and then a point out here. Like this point is this point in 2D space, and these two coordinate systems, we're just giving two different names for that same point. So for example, in a Cartesian coordinate system, right, we label it with its x and y values. But we could take that same point and label it with its radial distance and angle, and we would still be talking about this same point. And so the question is, given one of these labels, one of these coordinate pairs, how do I find the other one? And now if you look, you can take this and make a right triangle out of it. You can connect the origin and the point here like so. You can drop an extra line down here. And this line is perpendicular, so this would be 90 degrees. And so with this right triangle, it turns out that we can use a lot of the trigonometry, the SOHCAHTOA stuff you've probably seen in your previous work. To do this problem. It's actually kind of related to vectors. Like this math turns out to be the same as what you may have seen when working with vectors. Now, on this right triangle, notice that if we're starting at the origin to get to this point, left whatever the x value is, and then up whatever the y value is, think about it. This length right here would be x, right? Because we're going right that distance. And then this distance right there would be y because we're going up that distance. But then the direct distance from the origin to the point, that's r, right? And then in this specific case, because the point is in the first quadrant, it's the simplest case, 0 degrees is here, and then the angle we're talking about would be here, right? Theta. So now we've got a clean little SOHCAHTOA situation going on. This is a right triangle. We can do simple right triangle trigonometry. And so every time you could go and set up an equation using sine, cosine, or tangent and solve for stuff. But it's going to turn out the same every time, so let me give you some shortcuts. So first up, we've got converting from polar coordinates to Cartesian coordinates, as in they give you a polar coordinate, and we're going to rewrite it as a Cartesian coordinate. Well, you'll find that the math works out like so. X, you will find, is always equal to r, the radial distance, times the cosine of that angle theta. And then you will also find y equals r times sine theta. And by the way, this diagram, it's the simplest case, but no matter where the point is, this theta that they give you will always work with this. And these two things may be familiar to you if you have worked with vectors before. Because with vectors, there was a formula like, okay, you can take the magnitude of the vector and the angle of the vector and find a coordinate like the magnitude times cosine theta, comma, magnitude times sine of theta. And if you think about it, this is the exact situation. This point that we have out here, we could also just think of it as a vector starting at the origin and pointing to that point, so the head at the point there. And so we're using the exact same math that you would in a vector sort of situation to find x and y in terms of r and theta. And now going the other way from Cartesian to polar. So what if they give you a Cartesian coordinate and you need to rewrite it as a polar coordinate? Well, in that case, you would have x and y, and you can use the Pythagorean theorem to figure out what r is, again, like you would do with vectors. So the Pythagorean theorem in this case tells us r is the hypotenuse, so r squared equals x squared plus y squared. And then you could solve for r to get r by itself, as in you could square root both sides. So another way to write this would be, okay, r equals the square root of all this, right? X squared plus y squared. And now to find theta, though, that gets a little messy when you're talking about the point being in different quadrants. So to find theta, be sure to do a sketch and then use trigonometry, use SOHCAHTOA to figure out where all these different angles are, and use the sketch and SOHCAHTOA to figure out how many degrees we would need to go from 0 counterclockwise to get the correct angle. Okay, so first up we have convert the polar coordinates 17, 140 degrees to Cartesian coordinates. So remember, the answer is yet another set of coordinates, right? But for the same point in 2D space. And you know, going this way is easy because again, like we were just saying, x equals r times cosine of theta. Well, what's r? 17. Cosine of what's theta? 140 degrees. And then you plug this in your calculator. Clearly, this problem is having us work with degrees. So don't forget to put your calculator in degree mode. And if you do put it in your calculator with the correct degree mode, you'll get around negative 13.0228. And then y is r sine theta. So again, 17 sine 140, and that is around 10.9274. So this is the x value right here. This is the y value right here. So our final answer then is around negative 13.0228, comma, positive 10.9274. And that's the final answer. We're done. But let's sketch the situation to make sure that it makes sense. So 140 degrees, that's past 90, but not quite 180, and then 17. So, boom. And then the point is somewhere around here, right? So in polar coordinates, this is 17, comma, 140 degrees. Now, does negative 13 point something, comma, positive 10 point something make sense? Left 13, up 10. Yeah, that makes sense. And we're done. Okay, so now what about going the other way? Convert the Cartesian coordinates, negative 5, comma, negative 7, to polar coordinates. So again, going this way is a little harder, and you really should be sketching the situation. So negative 5, negative 7. Negative 5, negative 7, let's say that's around here. So, in Cartesian coordinates, negative 5, so left 5, negative 7, down 7. And then remember we said we can make a right triangle out of this. So here's where our r that we're trying to find is going to be. And then an extra line here, perpendicular. And remember, where's the negative 5 and the negative 7 on this triangle? So left 5, so this is our length of negative 5. Negative length is kind of weird, but, and then down, so negative 7 is here. And again, we want to find r, and we also want to find the angle. The angle, by the way, is the one starting at 0 going counterclockwise, so that's this angle right here. Now the r part is easy. We have r squared equals x squared plus y squared by the Pythagorean theorem. Then we have r squared, x is negative 5 squared plus y is negative 7 squared. You get r squared is 74, square root both sides, and you'll get, well, you could keep it exact if you want, square root of 74, which is around 8.6023. So there's the radius, the radial distance, but then theta. So, you know, keep in mind that again, the angle we're trying to find is this one right here from 0 going counterclockwise. But to ensure that you don't get confused, it might be beneficial just to keep it in terms of your right triangle first. So we're going to work on the angle, but maybe first you want to find like this angle in the right triangle and just use positive lengths. So positive 5 and positive 7, because now if we think about this angle and just positive lengths, that's just a normal SOHCAHTOA right triangle situation, right? So maybe we'll call this angle theta prime. And how would we use SOHCAHTOA to find that angle? Well, this 7 is opposite from the angle, and this 5 is adjacent. So we have tangent of this red angle is opposite over adjacent, so 7 over 5. And now how do we get theta by itself? We need to get that tan away, right? And to do that, you take the inverse tan of both sides. So this goes away, and you get the red angle in our right triangle is whatever the inverse tangent of 7 over 5 is. Turns out that's around 54.4623 degrees. So at the very least, we know that this red angle right here is this 54 point something. But if we just said the angle for this polar coordinate is 54.4623, like positive 54.46, then that would be out here, which is the wrong point, right? We need the point down here. So what you do is you can use the quadrants and the right triangle on our sketch to figure out what the actual angle should be. So we start at 0, and we go around 180 plus this little bit, which is the 54 we found, right? So our actual final angle, our final answer for the angle then is 180 plus that 54. So around 234.4623 degrees. And now if you think about it, that angle is in the right quadrant. We already had our radius. So then our final answer as a polar coordinate then is radius first, so around 8.6023. Again, we could also have written square root of 74 here. And then around 234.4623 degrees. And so there's that same point in 2D space as a polar coordinate. So that is it for this lesson. As always, if you have any questions or feedback, feel free to contact me.